Welcome to this problem walkthrough. In this session, we'll explore an exciting problem titled Delete Operation for Two Strings, which challenges us to analyze and optimize string operations. We'll dive into the approaches step by step and cover key concepts along the way. Let's get started. The problem we're solving is called Delete Operation for Two Strings. Here, you're given two strings, word1 and word2, and the goal is to make these two strings identical by deleting characters. The task is to determine the minimum number of deletions required. You can delete exactly one character at a time from either string. For the input, each string has a length between 1 and 500 and contains only lowercase English letters. The output is an integer representing the minimum number of deletion steps needed. For example, consider the input where word1 is C and word2 is eat. The output here is 2. This is because we can make both strings identical by deleting two characters. Specifically, we delete the S from C and the T from eat, leaving us with the common substring EA. Therefore, the minimum number of steps required is 2. Another example is when word1 is LeetCode and word2 is etco. In the LeetCode and etco example, the output is 4. To make the strings identical, we delete the characters L and D from LeetCode and the characters C and O from etco. This results in the common substring etco. Since 4 deletions are needed, the minimum number of steps is 4. Lastly, if word1 is A and word2 is B, the output is 2 because these strings share no common characters. When word1 is A and word2 is B, we delete A from the first string and B from the second, leaving both strings empty. Therefore, the minimum number of steps is 2. Now, let's consider some constraints and edge cases. Each string has a length between 1 and 500, and both contain only lowercase English letters. If the strings are already the same, no deletions are needed, so the result is 0. If one string is empty, the result is the length of the other string. If there are no common characters, we must delete all characters from both strings, making the result the sum of their lengths. Finally, for longer strings, the solution must handle up to 250,000 character comparisons efficiently to ensure good performance. To begin solving this problem, we can consider the brute force approach. The intuition here is fairly simple: generate all possible subsequences of the two strings and identify the largest common subsequence, or LCS. Once the LCS is determined, we can calculate the minimum number of deletions required by subtracting the length of the LCS from each string's length. Specifically, we would delete any characters from word1 that are not part of the LCS, and similarly for word2. However, this approach comes with significant challenges. Generating all subsequences involves exponential time complexity, specifically O(2 to the power of n *2 to the power of m, where n and m are the lengths of the two strings. This makes it computationally impractical for even moderately sized inputs. While the brute force method is conceptually straightforward, this inefficiency renders it unsuitable for solving the problem in real-world scenarios. To address this, we turn to a more optimized approach using dynamic programming. The optimized dynamic programming approach allows us to compute the LCS directly, bypassing the need to generate all subsequences. The key insight here is that the minimum deletions required can be derived from the formula: steps equals len, word1, plus len, word2, 2 * len, LCS. This works because the difference len, word1, len, LCS, tells us how many characters from word1 need to be deleted, and similarly for word2. To find the LCS efficiently, we use a DP table where DP, I, j, represents the length of the LCS for the first I characters of word1 and the first j characters of word2. The recurrence relation for this table is straightforward: if the characters at the current indices match, dp, I, j, equals dp, I1, j1, plus 1, meaning we extend the LCS. If they don't match, the LCS length is the maximum of excluding one character from either string, so dp, I, j, equals max, dp, I1, j, dp, I, j1. The time complexity of filling this table is O, n * m, which is efficient for strings of length up to the problem's constraints. While the space complexity is O, n * m, for the full table, it can be reduced to O, min, n, m, using a rolling array to store only the current and previous rows. The chosen strategy for this problem is the optimized dynamic programming approach. This method is significantly faster and more scalable than the brute force approach while remaining conceptually aligned with the problem requirements. By focusing on the LCS formulation, we achieve an elegant and efficient solution that is straightforward to implement. In terms of trade-offs, while a space-optimized version of the DP approach can reduce memory usage, it introduces additional implementation complexity. For most scenarios, the full DP table is sufficient unless memory constraints are particularly tight. Alternatively, a recursive solution with memoization could be employed, but it tends to have higher overhead compared to the iterative DP method. Overall, this approach balances clarity and efficiency, making it well-suited for handling large inputs up to the constraint of strings with 10 cubed characters each. Here, we define a 2D DP table, DP, where each cell DP, I, J, represents the LCS length for the substrings S1, 0, I1, and S2, 0, J1. The first step in this process is setting up the DP table for computation. To solve the problem of finding the minimum number of deletions required to make two strings identical, we need to approach it systematically. The strategy revolves around identifying the longest common subsequence, or LCS, of the two strings. The LCS represents the maximum sequence of characters that appear in the same order in both strings. Once we know the LCS length, the deletions required for each string can be calculated as the difference between the string's length and the LCS length. Combining these deletions gives the total deletions as n plus m, 2 LCS underscore length, where n and m are the lengths of the strings. To compute the LCS efficiently, we use dynamic programming. The DP table is initialized to a size of n plus 1 a6 m plus 1, where n and m are the lengths of the two strings. The first row and column are set to 0 because the LCS of any string with an empty string is always 0. After this initialization, we proceed to fill the DP table by iterating through each character pair of the two strings. For each combination of indices I and j, we check if the characters S1, I1, and S2, J1 match. If they do, the value at DP, I, J, is 1 plus DP, I1, J1, indicating that the current character extends the LCS. If the characters do not match, we take the maximum value between DP, I1, J, and DP, I, J1, which represents the best LCS length achievable by excluding the current character from one of the strings. Once the table is fully populated, the value at DP, n and m, represents the final LCS length for the two strings. This value is then used to compute the total deletions as n plus m, 2 DP, n, m. The process of filling the DP table leverages the fact that the LCS problem can be broken down into smaller overlapping subproblems. For example, computing LCS S1, 0, I, S2, 0, J, depends on solutions to smaller subproblems like LCS S1, 0, I1, S2, 0, J1. This overlapping nature makes dynamic programming an optimal choice for solving the problem. The recurrence relation ensures that solutions are built systematically for all substrings. The time complexity of this approach is O, n asterisk m, because the DP table has dimensions, n plus 1 x, m plus 1, and each cell computation is constant time. Additionally, we can optimize the space complexity from O, n asterisk m, to O, min, n, m, by maintaining only two rows of the table, the current and previous rows. This optimization significantly reduces memory usage while still allowing the algorithm to compute the LCS accurately. For implementation, we use a 2D array or, in the optimized version, two 1D arrays to capture the necessary values for the computation. Now, let's consider some important edge cases to ensure our algorithm handles all scenarios. First, if either string is empty, the LCS length is 0, and the number of deletions equals the length of the non-empty string. Second, if the two strings are identical, the LCS is the entire string, and no deletions are required. Finally, if the two strings share no common characters, the LCS length is 0, and the deletions required will simply equal the sum of the lengths of both strings. To better understand the mechanics, let's walk through an example. Suppose the two input strings are S1 equals ABCD and S2 equals ACE. We start by initializing a DP table with dimensions 6 by 4, because the lengths of S1 and S2 are 5 and 3, respectively. Initially, the table is filled with zeros, representing the base case where the LCS for any string with an empty string is 0. With the table initialized, we begin filling it by comparing characters of S1 and S2. At I equals 1, j equals 1, the characters s1, 0, and s2, 0, both equal up, so we set dp, 1, 1, equals 1. At I equals 1, j equals 2, the characters do not match, so dp, 1, 2, equals max, dp, 0, 2, dp, 1, 1, equals 1. This process continues, comparing characters and updating the table based on whether characters match or not. After completing all iterations, the final dp table looks like this: 0, 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 2, 0, 1, 1, 2, 0, 1, 1, 3. The value at dp, 5, 3, which is 3, represents the LCS length of the two strings. Using this LCS length, we calculate the total deletions as 5 plus 3, 2 asterisk 3 equals 2. This means 2 deletions are required to make the strings identical. Finally, the algorithm outputs the result. The minimum number of deletions required to make the two strings identical is 2. This result was derived by efficiently computing the LCS using dynamic programming, ensuring optimal performance for any input size. By understanding the principles of LCS computation and leveraging edge case handling, this algorithm provides a robust solution to the problem. This Python implementation solves LeetCode problem number 583, delete operation for two strings, using a dynamic programming approach. The goal is to compute the minimum number of deletions required to make two strings identical. First, the function minDistance is defined, which takes two input strings word1 and word2. We calculate their lengths, n and m, respectively. Next, a 2D list dp of dimensions, n plus 1 and x, m plus 1, is initialized with zeros. The purpose of dp, I, j, is to store the length of the longest common subsequence, LCS, between the first I characters of word 1 and the first j characters of word 2. The nested loop iterates over each character of word 1 and word 2. If the characters match, word 1, I1, equals word 2, j1, then the LCS length is incremented by 1 from the previous diagonal value, dp, I1, j1, plus 1. If the characters do not match, the maximum LCS value from the previous row or column is taken, max, dp, I1, j, dp, I, j1. After populating the dp table, the length of the LCS is stored in LCS_length, which is dp, n, m. Finally, the minimum deletions required to make the strings identical is calculated as n LCS_length plus m LCS_length. This formula represents the total characters in both strings minus twice the LCS length, as the LCS characters are preserved. This approach is efficient with a time complexity of O, n asterisk m, and a space complexity of O, n asterisk m, where n and m are the lengths of the input strings. The solution ensures correctness by dynamically computing the LCS for all substrings, making it robust for all edge cases, including empty strings. This is the Java implementation for LeetCode problem number 583, delete operation for two strings. The solution mirrors the Python logic by using dynamic programming to calculate the longest common subsequence, LCS, of the two strings. The minimum number of deletions required is derived from the lengths of the two strings minus twice the LCS length. Key differences in Java include explicit type declarations, the use of the charet method for string indexing, and the math.max function for comparisons. To solve the problem delete operation for two strings, we need to determine the minimum number of deletions required to make two strings identical. The central idea is to find the longest common subsequence, or LCS, between the two strings. By knowing the LCS length, we can calculate the deletions needed for each string to reduce them to just this common subsequence. For example, if we have the strings c and eat, we start by initializing some variables. The lengths of the two strings, n and m, are both 3. We then create a 2D dynamic programming table, or DP table, of size, n plus 1, x, m plus 1, initialized to 0. This table helps us systematically calculate the length of the LCS. At this point, the DP table is just filled with zeros, and our next step is to traverse both strings to populate it based on the matches or mismatches between their characters. Now, we begin filling the DP table by comparing characters from word 1 and word 2 one pair at a time. For I equals 1 and j equals 1, we compare s from word 1 and e from word 2. Since they don't match, the value at dp, 1, 1, is the maximum of the values above it and to its left, which is 0. Similarly, for I equals 1 and j equals 2, we compare s from word 1 and a from word 2, and again, they don't match, so dp 1, 2 remains 0. The same happens for I equals 1 and j equals 3 with s and t. As we continue this process, we eventually find matches, such as when e from both strings aligns, and we update the table accordingly. By the end, the dp table is filled, and the bottom right value, dp n gives us the LCS length, which is 2. Using this, we calculate the minimum deletions as n LCS plus m LCS, which equals 2 for this example. In another example, consider word 1 equals ABC and word 2 equals def. Here, neither string has any common characters, so the process of filling the dp table is straightforward. We initialize the table with zeros, and as we traverse the strings, no matches are found. This means all values in the dp table remain 0. The LCS length, therefore, is 0, which is the value at dp n m. To compute the minimum deletions, we use the formula n LCS plus m LCS, which in this case equals 3 0 plus 3 to 0 equals 6. This means all characters from both strings need to be deleted to make them identical. Finally, let's examine a more complex example where word 1 equals intention and word 2 equals execution. In this case, the strings share several common characters, but they are not contiguous. We initialize a 9 by 9 dp table, and as we traverse the strings, we update the table based on matches. For example, when we find matching characters like E or N, we increment the LCS length in the dp table. After processing all characters, the final table shows an LCS length of 5, which represents the longest subsequence shared by both strings. Using this LCS length, the minimum deletions are calculated as n LCS plus m LCS equals 9 5 plus 9 to 5 equals 8. This means 8 deletions are needed to make the two strings identical. The time complexity of this solution revolves around the use of dynamic programming to compute the minimum number of deletions required to make two strings identical. To begin, we initialize a 2D dynamic programming table, or DP table, of size n plus 1 by n plus 1, where n and m are the lengths of the two input strings, word 1 and word 2. This initialization step involves allocating memory and setting all cells to 0, which takes O and asterisk m time due to the size of the table. Next, we fill the DP table by iterating through all possible index pairs of the two strings using nested loops. For each pair of indices, we compare the corresponding characters in the two strings. If the characters match, the value in the DP table is updated to reflect an extension of the common subsequence. If they do not match, we take the maximum value from the previous states. Since each cell computation is constant time and there are n plus 1 asterisk m plus 1 cells, this step also has a time complexity of O n asterisk m. Once the DP table is fully populated, we can compute the result. The length of the longest common subsequence, or LCS, is stored in the bottom right cell of the table dp n m. Using this value, we calculate the minimum number of deletions required as the sum of characters in both strings that are not part of the LCS. This is computed in O1 time using the formula n LCS underscore length plus m LCS underscore length. Overall, the dominant factor in the time complexity is filling the DP table, which takes O n asterisk m. For space complexity, the primary contributor is the DP table itself, which requires O n asterisk m space since it stores an integer value for each of its n plus 1 asterisk m plus 1 cells. Additionally, a few auxiliary variables such as loop counters and the length of the LCS require only O1 space. Therefore, the total space complexity is also O n asterisk m. This solution can be further optimized in terms of space usage. While the full DP table has a space complexity of O n asterisk m, the problem only requires access to the values from the current and previous rows of the table at any given time. This means we can reduce the space complexity to O, min, n and m by maintaining only 2 rows instead of the entire table. Comparing this optimized approach to a brute force solution highlights the efficiency of dynamic programming. A naive approach would involve generating all possible subsequences of both strings and comparing them to find the longest common subsequence. This brute force method has an exponential time complexity of O, 2 to the power of n asterisk 2 to the power of m, making it impractical for larger strings. In contrast, the dynamic programming approach reduces this to O and *m, which is a significant improvement in both efficiency and feasibility. When analyzing the best, average, and worst cases, the time complexity of this solution consistently remains O and *m. This is because the double loop used to fill the DP table iterates through all cells regardless of the specific input strings. Similarly, the space complexity is O and *m when using the full DP table, but it can be optimized to O, min, n, m, as discussed earlier. To confirm the time complexity mathematically, we observe that the nested loops iterate over all combinations of I and j, where I ranges from 1 to n and j ranges from 1 to m. This results in n *m iterations in total. Since each iteration performs a constant amount of work, such as comparing characters and updating the DP table, the total computational effort is proportional to n *m. Thus, the time complexity is conclusively O and *m. When solving problems like this one, it's essential to be mindful of common mistakes that can trip you up. First, you need to handle edge cases properly, like when one or both strings are empty, or when the strings share no common subsequence at all. These scenarios often lead to incorrect results if not explicitly tested. Another key pitfall is confusing subsequences with substrings. Remember, a subsequence allows characters to be non-contiguous, whereas substrings require continuity. This distinction is critical to solving the problem correctly. Additionally, while recursion might feel intuitive, using it without memoization can make the solution impractically slow, especially for larger inputs, due to exponential time complexity. Instead, dynamic programming or memoization is essential for efficiency. Speaking of dynamic programming, initializing the DP table correctly is another area where mistakes often occur. The first row and column should be filled with zeros, representing comparisons with an empty string. Missing this step leads to errors. Finally, index handling deserves attention, as off by one errors are common when transitioning between DP states or iterating through strings. Careful tracking of indices can save you from subtle yet frustrating bugs. Now, let's consider some key insights that are particularly relevant for interviews. One optimization to keep in mind is reducing the space complexity of the DP solution. Instead of using an O and *m table, you can maintain only 2 rows at a time, reducing space usage to O, min, n and m. This kind of optimization often earns bonus points with interviewers. It's also important to recognize that the longest common subsequence framework is a foundation for many related problems, such as finding the longest palindromic subsequence or determining minimum insertions to make a string palindrome. Mastering this framework enables you to adapt quickly to variations. Additionally, interviewers may ask you to contrast the inefficiency of brute force approaches, which have a time complexity of O, 2 n plus m, with the much more efficient O and *m that dynamic programming or memoization offers. Beyond just implementing the solution, explaining the intuition behind the DP state transition is crucial. For example, you should be able to articulate why DP, I, j, depends on DP, I1, j1, plus 1 when characters match, and on max, DP, I1, j, DP, I, j1 when they don't. Finally, keep in mind that this problem has strong connections to other challenges, like LeetCode 1143, 516, and 1092, which you can explore to deepen your understanding. There are also alternative approaches and trade-offs to consider. A recursive approach with memoization is often seen as intuitive, but it comes with higher overhead because of recursive calls. While its time complexity is O and *m, the space complexity can go up to O n plus m due to the recursion stack. On the other hand, an iterative DP solution is more efficient in terms of space and is generally preferred in interviews for its clarity and practicality. For even better space efficiency, you can use a space-optimized DP approach that only keeps 2 rows of the DP table. This reduces space usage to O, min, n and m, although it's a bit more challenging to implement. Discussing this approach in an interview can reflect a deeper understanding of the problem. Ultimately, problems like this one emphasize the importance of breaking down a complex problem into smaller, manageable subproblems. Understanding how these subproblems connect to form the overall solution is a key insight. Additionally, fluency in the LCS framework opens doors to solving related problems, such as those involving string similarity, edit distance, and sequence alignment. This makes mastering LCS techniques an invaluable skill in tackling a variety of challenges. Great job! We've covered the problem, explored its solutions, and learned some valuable techniques like dynamic programming. Remember, practice is key to mastering these concepts. Thanks for watching. Don't forget to like, share, and subscribe for more content. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!